All right, this is Chapter 9 quiz on fluids. A tendon in your arm without any pressure has a length of 0.1 meters. The cross-section area is 0.75 square centimeters. How much does it stretch? So here we're looking at the stress, force over area, is equal to the Young's modulus times the strain, delta L over L. And we're looking for delta L, so I'm just going to solve this for delta L. The force is, what is the force? 100 newtons. The length of your tendon is 10 centimeters or 0.1 meters. The cross-sectional area, I give it to you in square meters, which we need it, so 7.5 times 10 to the minus 5 square meters, times the Young's modulus, which is 2 times 10 to the 7 pascals, and that's 10. I get 0.0067, or just call it 0.007 meters, which is equal to 0.7 centimeters. So the answer is B. Block of unknown density is floating in fluid, such as this figure. What can you say about the density of this block? Well, to float, the density has to be less than the fluid, so the block is less dense than the fluid. Air is trapped above water. A rigid container is shown in this figure. What is the air pressure? Noting I have an air pressure here, P naught, equal to 1 atmosphere. And I would say P equals P naught plus rho GH. P naught is 1 atmosphere, that's 1 times 10 to the 5th pascals, plus the density of water, which is 1,000. You can look on your density table to find that. 9.8 times 9, and that's going to be 1.9 times 10 to the 5th pascals, which is going to be 1.9 atmospheres, which is A. Here, this figure shows a manometer, which is filled with mercury. I want to know what is the pressure of the methane gas. It gives the temperature. I don't really need the temperature. I want to know what is the pressure. Now, I have a height of mercury right there, H, that can tell me the pressure. Remember, the manometer is P naught plus or minus rho GH. And so I want to ask myself, is P here bigger or smaller than P naught? I know that P, in order to have this setup, has to be less than the atmospheric pressure, because this atmospheric pressure is pushing this column down. It's bigger than the pressure of the methane. So let's see, I can look at that. Since I know P naught is 1 times 10 to the 5th pascals, or 100,000 pascals, I know that P has to be less than that, and the only answer that is less than 100,000 is 93,000. So let's go ahead and we'll work through it. So we get 100,000. Because P is less than P naught, I know this is minus. The density is 13,600. G is 9.8. And H is 0.05 meters. That's 5 centimeters. And that's equal to 93,000 pascals. Mass of 1 kilogram. It's halfway submerged in water. What is the density of the object? Okay, so I have this block. It floats halfway. So I have the volume over 2 is submerged. I want to know the density of the object. Now I know that the forces acting on this are the buoyant force and the weight. And because it's floating, I know that the buoyant force is equal to the weight. So I can say FB equals FW. FB is the density of the fluid times the volume of the object divided by 2, because that's the volume that's submerged, times G, and that's equal to M times G. Notice my G's canceled. And this is the mass of the block. This is the volume of the block. And so I can write this in this way. I can say the density of the fluid divided by 2 is equal to the mass over volume. And that's equal to the density of the object. So the density of this object is half the density of the fluid. This is water, so it's D, 500. It's 1,000, so the density of water divided by 2, which is 500. Okay, so I have a 10 kilogram mass of wood that floats fully submerged in a tank of water. What is the volume of the wooden block? All right. In order for it to float fully submerged, this is a little bit of a misleading question. In order for it to float fully submerged, I have this block. It has to be attached in some way to the bottom, so it has an additional force acting upon it. But nonetheless, it works out correctly. So I can say that the buoyant force is equal to the density of the fluid times the volume of the object times G, and that this has to equal the weight. And that will give you the right answer, but that's not entirely true. Oh, actually, never mind. I'm sorry. We can do this in an entirely easier way. I have the density of the wood, and I have the mass of the wood, so I can volume. So density is mass over volume. So volume is density, or excuse me, is mass over density. The mass is 10 kilograms over 900 kilograms per cubic meter. And so that's equal to 10 over 900, which is about, what, 0.01 or so. So C is the right answer. That's the easiest way. But if it is submerged in a tank, since it's less dense than water, it would tend to float up to the surface and not be fully submerged. But if it is fully submerged, that means that it has the buoyant force acting on it. It also has the weight, and then it has some additional force, some tension in a string or something that's pushing it down. The following figure shows top half of a pipe carrying water. The standpipes are used to measure the pressure. So if you have this open pipe, you can measure the pressure just based on the height of the column that's in it. All right, and remember, this works like a manometer. We use rho GH. And so the one with the bigger height has the bigger pressure. So this has a big pressure, this has a smaller pressure, and this has a little bitty pressure because of the varying heights in the standpipes. So the pressure is greatest at point A. And then in this next question, I want to know which of the following best describes the shape of the portion of the pipe, which isn't shown in this figure. So does the shape narrow as it goes from this direction? Does it narrow as it goes from there to there? Does it get wider like this? Or does it just go straight? Which of those is it? Well, I know I have a big pressure here, and so that means that I have to have a small velocity. And I have a small pressure here, so that means I have to have a big velocity. All right, that's from Bernoulli's equation. High velocity gives you low pressure. And if I go to my continuity equation, A1V1 equals A2V2, if I have a big velocity, if this is big, that means my area has to be small. So that means that my pipe has to be narrowing from left to right. So I have a big velocity here, which gives me a low pressure. So let's see which the pipe narrows from left to right. Let's see. Material has a higher density than another. Does it mean the molecules of the first must be more massive than those of the second? The answer is no, that it doesn't matter about the density. The density is dependent on how closely packed those molecules are, not on the actual mass of the molecules. Consider what happens when you push both a pin and a blunt end of a pin, so like a push pin or a writing pin. What will determine whether your skin is punctured? The pressure is the relevant thing. You can push with the same force on both and not puncture your skin with a writing pin, but do with a push pin. It's because of the pressure, the area is a lot smaller. Walking out on a frozen lake, you begin to hear the ice cracking beneath you. Best strategy is to lie down flat. All right, pressure equals force over area. If you lie down flat, you increase that area and decrease the pressure. Swimming near the bottom of a pool, you'll let out a small bubble of air. As that bubble of air rises, it will get bigger and bigger because the pressure will decrease, allowing it to expand into a greater volume. So the diameter will increase, that's C. 3 containers are filled with the same water to the same height. Now, to find the greatest total force, we need to find the pressure. Pressure is force over area. These all have the same area, and they're all the same height, all right? So that means that they have the same pressure, which is rho GH. And because they have the same area, they're all going to have the same force at the bottom. So all 3 are equal. When a hole is made in the side of a Coke can holding water, water flows out and follows a parabolic trajectory. If it's dropped in free fall, what happens? Well, the reason that it comes out is because it's in free fall, or excuse me, when it's not in free fall, it has this weight, which causes a pressure differential. So you get this high pressure down at the bottom because of the weight of the column that sits atop it. But when it's in free fall, it's weightless. That acceleration due to gravity is taken away from it. And when it's weightless, it no longer has that pressure differential, so it's going to stop. When you drink a liquid through a straw, which of these items is primarily responsible? Or if I have a liquid in a cup, I have a pressure, a very large pressure due to the atmosphere that's pushing this liquid up into the straw and into your mouth. Now, your mouth does play a role, but not nearly the role that the atmospheric pressure has. So the atmospheric pressure is what primarily drives that liquid up into your cup. Right? You merely just provide a small pressure differential of a pressure that's slightly smaller than the atmospheric pressure. Put a straw in a glass of water and place your finger so no air can get in or out. Then you lift the straw from the liquid. This is right before you sling it at somebody. How does the air pressure in the upper part compare to the atmospheric air pressure? Well, P has to be less than PA. Right? If it was equal, the water would just fall out. If it was greater, it would fling out vigorously. So the answer is less than, that's C. Mercury barometer, you get 760 millimeters. What if you make a larger diameter barometer? It's going to be the same, C. Pressure for a barometer is equal to rho GH. Notice that it's not dependent upon the area at all. It's only dependent upon the height of the barometer and not the area or the diameter. You don't use alcohol in a barometer because mercury is more dense. You had a homework problem like this where you use wine, I think, or water in a barometer, and you get a very tall, you get a very large height of column, like 10 meters. So use it because it's more dense. Because remember, P is equal to rho GH. So if this is really big, that means your height can be very small. Imagine holding 2 identical bricks and placed under water. Brick 1 is just beneath. Brick 2 is 2 feet down. What force is needed to hold brick 2 in place? It's going to be the same. These are both going to experience the same forces. I have the buoyant force acting on both, and then I have their weight acting on both. So let me be. Boat carrying a large chunk of steel is floating on a lake. The chunk is thrown overboard and sinks. What happens to the water level in the lake with respect to the shore? The water level of the lake is going to drop. The reason for this is that the steel displaces more water and it's floating. In the boat than when it is at the bottom. And at the bottom, actually, the buoyant force holding it up is quite a bit smaller than the buoyant force when it's in the boat. If you look at this, if you actually look at the concept test, there's a figure that might help you understand this a little bit better. So take a look at that. If you have questions, please let me know. Helium balloon and air-filled glass jar floats to the top. If the air is placed with helium, what will happen to the helium balloon? So I have this glass jar. It's filled with air. And in the case of the air, if I have a helium balloon, it's going to look like it'll go up to the top. The reason is because the buoyant force is fairly big, is less than the force weight of the balloon. However, if I replace that jar with helium inside, I have helium inside the balloon, it's going to sink. That's because the buoyant force is less than the weight. Now remember, the weight of this balloon includes the mass of the balloon times g plus the mass of the gas inside the balloon times g, which is going to be helium that will sink to the bottom because it has negative buoyancy. Now the jar is lifted off the table, but it remains inverted. So in this case, I would take either B or C for this answer, actually. If I have helium here, the helium is not going to come out of the jar. Your balloon, I think in the actual concept test it says that it stays right inside the jar like that. But in reality, the balloon is going to sort of stick out the bottom of the jar just a little bit, right? Because it's actually, the weight of the balloon is actually a little bit heavier than the buoyant force of the balloon holding it up. So not quite enough to hold it fully inside the jar, but mostly inside the jar because of that added weight of the balloon and of the helium. All right, 2 beakers are filled to the rim with water. A wooden block is placed in the second beaker so it floats. Some of the water will overflow the beaker. Both beakers are weighed. Which scale reads a larger weight? They're both going to read the same weight because this block displaces, the buoyant force of that block is equal to the, the buoyant force of the block is equal to the weight of the block. And so it's displaced the volume of water that's equal to its weight. So that water is now gone and it's been instead replaced by the weight of the block. So they're going to both have the same weight. All right, how would these scenarios change from the Earth to the Moon? It's going to be the same. The reason is because the buoyant force is equal to the weight. That's rho Vg equals mg. Notice that the g's cancel. So it doesn't matter if you're on another planet, your buoyancy will still be the same because it's not related to, at least in this case, not related to the acceleration of gravity. A water flows through a 1 centimeter pipe connected to a 0.5 centimeter pipe. Like that. The speed in the 0.5 centimeter pipe is double. So I have a big velocity, small velocity. That comes from our equation of continuity. If this goes down by a factor of 2, this goes up by a factor of 2. D. Blood platelet drifts along with a flow. Here my velocity goes up from the equation of continuity. From Bernoulli's principle, the pressure decreases, so B. Person's blood pressure is generally measured on the arm. What happens if you measure it on the leg? This is a very strange person. All right, so if I measure it here, I get a certain pressure. If I measure it down here, remember our pressure is equal to rho GH. Here I have this column of blood, you can think of it as sitting on top of it, and that's going to increase the blood pressure. So the blood pressure will be higher. That's C. How is the smoke drawn up the chimney affected when there's a wind blowing outside? All right, here's my chimney. That's smoke coming up in here. And then if I have a wind current flowing here, I have a high velocity, and that means I have a low pressure. So if I have a low pressure, this smoke is going to be pulled out of the chimney because it's like I have a high pressure down here that's pushing it up. I have that pressure differential. So the smoke rises more rapidly in the chimney, that's A.